Hello, everyone, and welcome to our very first lecture on sets, which is chapter 2. And speaking of the textbook, you have access to the textbook on MyMathLab, so the place where you do your homework. To the left, you should see a button that says resources or textbook, ebook, and then I don't think you would need to access to the textbook if you understand my lectures and you go and do your homework, but just in case you're going to have something to read, you can always do that. So sets. So this chapter will do it through several sections, and this is section 2.1. We'll be talking about the concepts of a set. Okay, well, after you finish this, you should be able to understand how to describe a set, to write a set in what's called a raster form or set builder form. And then you are going to understand some concepts related to finite sets and infinite sets, and how can you tell if two sets are equal or equivalent. We'll talk about the cardinality of a set, which is just the number of elements of a set. And then we'll be talking about some special sets, namely the empty set. Sometimes it's called the null set or the universal set. But let's get started. So what is a set? It's just a collection of objects. And when I say an object, it could be really anything. You have a set, you can have a set that has a cup of coffee and a cell phone and basketball. So this set has 3 objects. You can have a set that has numbers. So these objects, usually we call them elements of a set or members of the set. So we have 3 methods to indicate a set. Either you describe the set, just write a small paragraph or description of the set. You can represent your set sometimes in what's called raster form when you have a finite set or even infinite set. So we'll see that through some examples. Or we have what's called a set builder notation, where you don't explicitly write down the objects, but you write a mathematical expression that will allow you to get those elements. For now, don't worry about anything. We'll take it one step at a time. So a set should be well defined. So when you say, well, here is a set, then you should be able to provide a clear definition of the set. So namely, what are the elements of the set? For example, I may have the set of US presidents. So take all the US presidents and put them as elements of a set. And you can call this set the set of US presidents. Or you can have, for example, here's an exercise that tells you to write a description of the set containing the elements January, February, all the way till December. So what would you do, or what would you say? You can say this is the set of the months of the year. Yeah, if someone asks you to describe this set, then we would say this is the set of all the months of the year. So when it comes to description, again, it just uses common sense and says some words to describe the nature of the objects, unless you have a crazy set that has some objects that are not related. In this situation, you may say, well, here's a set that has these elements and you list them all. Yeah. Okay, the raster form. The raster form is a set notation when you open a curly bracket and you list all the elements one after the other. So again, we are going to use these symbols. So the opening brackets denotes the start of the set, and the closing bracket denotes the end of the set. For example, you can have, this is the set of 3 elements, which are here in this example, 1, 2, and 3. Those commas are just delimiters. So you cannot say, well, I have the set of 1 and a comma and 2 and a comma and 3. No, you say I have a set of the elements, or whose elements are 1, 2, and 3. And by the way, if you list them in another order, you still talk about the same sets. So in the order in which you list the elements of a set does not matter. In other disciplines of mathematics, we have like a special kind of sets. We don't call them, of course, sets, where the order matters. We're not going to deal with that this semester. Again, please, this is kind of notation. So we use brackets, curly braces, not parentheses, and not square brackets. So when you name a sets, well, you can have several sets. Well, how can you make the difference between them? Well, we usually use capital letters. Just like algebra, we use lowercase x to say something, lowercase p to say, for example, the price of an item, lowercase t to denote time. Well, for sets we can use, or it is like the like you hear you read here. We generally, but you of course you are welcome to name your set the way you want. But as a common, I would say, practice, we use capital letters to name sets. For example, we use the capital N to say this is the set of natural numbers or counting numbers. What are the counting numbers or natural numbers? Are 1, 2, 3, 4, 5, 6, and on and on and on. So the set N can be denoted in raster form like this. Again, here's the curly bracket or brace, 1, 2, 3, 4, and dot, dot, dot. Those dot, dot, dot are not denoting the sixth element of the set. They are just to show you it goes like this. It's just enough to see the pattern. If they put 1, 2, dot, 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 you may say, well, what's going to be next set? So 1, 2, 3, 4, 5, most likely, if you are asked to, or someone is asked to give the next element, that person will say 6. Okay. Okay, here is an example. Can you write the raster form of the set A of the natural numbers that are less than 6? What are the natural numbers less than 6? Well, they are 1, 2, 3, 4, 5. So the set A will be, again, in raster form, 1, 2, 3, 4, 5. This is simple stuff, right? So just pay attention to the notation. Well, here's another example. So set B is the set of all natural numbers less than or equal to 45. Then we can do 1, 2, 3, 4, 5, 1, 2, 3, 4, and put dot, 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 45. Or you can put 1, 2, 3, dot, 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 all the way to 45. It does not matter how you present this. Or if you have time and you have enough ink, you can list them all, but it's going to be too much, and you don't have to. You put 1, 2, 3, 4, 5, 6, 7, 8, all separated by commas all the way 45, and you close your bracket. You don't have to do that. Just use those 3 dots like you see on the slide to say it goes on and on till it hits 45. How about the set P of planets in Earth's solar system? Well, here they are, right? Since we don't have enough space, so we want to the next line. So Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. How many elements are in there? 1, 2, 3, 4, 5, 6, 7, 8. So we are going to say that this set P is having 8 elements, yeah, like I just said, or of cardinality 8. Or the cardinal of set P is 8. It's just a fancy word to say the number of elements of a set. Now, some symbols. So in mathematics, people use symbols to avoid writing a lot of things. And you need to keep in mind that mathematics a long time ago, people would write mathematics just like writing a novel, writing a story or something. They used all, like say, Greek letters, and a math book will look like a book with paragraphs. And after that, mathematics gets bigger and more fields, a lot of stuff. And then people would write a lot just to say a little small thing. And then people started, mathematicians, they said, well, what can we just use symbols to cut a little bit of this writing thing? So, and they use symbols. For example, this symbol like E, well, it's not like a capital E. How it looks in front of your eyes now. It's just like a curved E. So we are going to use this symbol to say is an element of. So this is just to indicate the membership in a set. For example, or before I give you an example, if you slash it with a slash, if you write a slash through it, you say is not an element of, just like an equal sign. Remember we put equal sign. So this is equal to, oops, I don't know why this is not right. This is equal to, and this is not equal to. Yeah. So use it. So this is an element of, this is not an element of. Okay, well, I'll give you an example. If I say, for example, is 3 an element of the set 7, 8, and 10? Saying is 3 an element of, so this is false because 3 is not an element of. Can I say, for example, A, is it an element, not an element of A, B, C? This is also false because A is an element. Here it is. How about 3 is not an element of 1, 7, and 19? Well, this is true because 3 is not an element of 1, 7, 19. So it's a, when you use the symbol, it's just to indicate whether something is an element of or not. So a set builder notation, remember you can describe a set, you can use a raster form, or you can use what's called a set builder notation or a generator notation. I'll tell you why they call it this way. I'll give you an example. You see this set 1, 2, 3, 4, 5? I could have written that this way. I know it's going to be a little bit mathier now, but trust me, it's simple. Don't freak out or don't say, oh, what's this? Well, let's read this all together. It said set B is a set of elements, let's call them X. You see that bar here? You read it such that or so that X is an element of N. And remember, we use the capital N to denote the set of natural numbers. And X less than 6. Basically, they tell you B is a set of natural numbers that are less than 6. That's what it is. So this is called a set notation form. So I could have written B this way. So what are the natural numbers that are less than 6? 1, 2, 3, 4, and 5. So these two things are the same. It's just the set builder notation sometimes is useful when you cannot use the raster form. For example, can you list me the set of all numbers between 1 and 5? When I say all numbers, I don't mean natural numbers. Between 1 and 5. Okay, let me start listing all the set between 1 and 5. Let's start at 1 and finish with 5. Can you use the raster form? What are the numbers that are between 1 and 5? Well, there are infinitely many. 1 and 1.11 and 1.1112 and 1.0003 and 2.1119. So you cannot list all the real numbers between 1 and 5 in raster form. It's not going to happen, right? This is not. So that's why we use the set builder form. So in the set builder form, I can call this set, I don't know, let's say capital, let's say L. Let's say the set X says that X is a real number. This is the notation for real numbers. Again, N, we're using capital N to say the set of natural numbers. We use capital R. Sometimes we use a double bar here. It's just it's a matter of choice. Or you can use just capital R. So capital N, it's a kind of like a reserved letter for natural numbers. Capital R is a reserved letter for real numbers, right? And then I'm going to say X less or equal to 5. So what does this mean? It means I'm going to take all the real numbers that are less or equal to 5. But of course, I need to start. I'm going to say, I forget that, and X is greater or equal to 1. That's very important because I said I'm going to start at 1 and finish at 5. So this is the set builder notation of my set L. And if I'm asked to do the raster form, I can't do it. What would you put? Where would you put 1 and then 1.1 and put dot, dot, dot all the way 5? Well, between 1 and 1.1, you know how many elements I missed? Or I skipped? Infinitely many. Like what? Like 1.001, 1.01, 1.00334, and on and on and on. So I cannot use the raster form. However, when I deal with natural numbers, 1, 2, 3, 4, I mean, how many natural numbers between 1 and 2? None. There's no natural number between 1 and 2. Right after 1, you have 2. And sometimes like this exercise A, sometimes you can use both the raster form and the set builder form. Or I can say X, so B, going back to this example here, B is the set of natural numbers and what? X less or equal to 5. So a natural number that is less than 6 is less or equal to 5, again, because there are no numbers between 5 and 6. To be correct, there are no natural numbers between 5 and 6. So right after 5, you get 6. So what are the natural numbers that are less or equal to 5? Well, they are the same natural numbers that are less than 6. Here's another example. The set of all X, such as X is a natural number, and X is less than 6. Well, Well, I think this is a wrong, this is a wrong exercise here. The set of all, well, again, if I need to read this correctly, when you say the set of all x such that x is a natural number and x less than 6, they're talking about the set B. We're still talking about the same exercise. It's just this B here is misleading. Okay, here's another example now. Write down the set A, they called A, they are free to call whatever, just stay away from N, right? Capital N, because capital N again means the set of natural numbers. So what are the natural numbers that are between 2 and 8, including 2? So how can you do the raster form? Well, they are 2, 3, 4, 5, 6, 7, right? Don't go all the way to 8 because less than 8. If it says less or equal to 8, of course, I would have listed 8 as well. So here is a solution: 2, 3, 4, 5, 6, and 7. And of course, again, you don't have to list them in this order. You can put 3, 5, 2, 3, 6, you can list these elements at any order, doesn't matter. But why would you? Just stay simple, list them in order. It's easier to read. Okay, now we move to what's called a finite set. What's a finite set? Is a set that has finite number of elements. Like this set here. This set is finite because it has a limited number of elements, right? 2, 3, 4, 5, 6, 7. How many elements? 1, 2, 3, 4, 5, 6. So this has 6 elements. But if you take, for example, the set N, the capital N, it's a set by itself, but it has infinitely many elements. And we call it an infinite set. That's what it is. So again, like I said, a set that contains no elements or the number of elements in a set that is a natural number. So they say here, so we need to pay attention to this. A set that contains no elements, can we have that? Yes, and it's called a null set, right? So if I ask you to give me an example of a finite set, you may say, well, here's a set that has no element. Yes, it's a finite set. It has 0 elements, or it has a limited number of elements. Yeah, maybe we get some examples. Here's a set B. It's a finite set. It has 5 elements, right? 1, 2, 3, 4, 5. Now, what's an infinite set? An infinite set is a set that has infinitely many elements. That's what it is. You cannot say this another way, I guess. So, like the set of all natural numbers. Or basically, a set that is not finite, it must be infinite, right? Well, 2 sets are equal if they are having the same number of elements. 2 sets are equal when they have the same elements, literally the same elements. Example, the set 1, 2, 3 is the set 3, 1, 2. As I told you, if you can write the elements of a set at any order, you still be talking about the same set. In this case situation, we say these sets are equal. Here's another example. I'm going to squeeze an example here. If you say, for example, the set of x such that x is a natural number and x less or equal to 2 is the same thing as the set 1, 2. So these 2 sets are the same. You can use what's called the set builder form, or you can use the raster form. These are equal sets. The cardinal number of a set, you can call it N of A, if you're talking about the set A, is the number of elements of set A. So if I go back to this example, suppose I call this set C, for example. This set C. What will be N of C? What's the cardinal of C? Should be a C here. Let me see if I can delete this. Oh, here's a. So what will be N of C? Will be 2. Means how many elements? What's the cardinal of set C? Means, in simpler words, it means how many elements in that set C. Well, it has 2 elements. So A, set A 1, 2, 3. So therefore, N of A is, or let's say B, England, Brazil, and Japan. All these sets, they have the same cardinal number, means they all have the same number of objects. They are not necessarily equal to each other. Actually, they're called equivalent. We'll see that say in a moment. We're going to see this in a moment. So the cardinal of A is 3, and the cardinal of B is 3. Are they equal? No. Well, 1, 2, 3 is not equal to England, Brazil, and Japan, right? So in notation, N of A is equal to N of B. So now it's time to introduce this definition of equivalent sets. Well, set A, if you have two sets, they are said, or they are called equivalent if they have the same number of elements, if they have the same cardinality. For example, in the example we have here, are A and B equivalent? The answer is yes, simply because they have the same number of elements. How many elements in A? 3 elements, which are 1, 2, 3. How many elements in B? Well, 3, which are England, Brazil, Japan. I can give you another equivalent set to A and B. Let's say set K equals, I don't know, A and a bird and 4. Oops. These sets are all equivalent. Why? Because they have the same number of elements. Example, right? ABC, the set D that has ABC in it, the set E has apple, orange, and pear. They are equivalent because they have the same cardinal. So therefore, we call them equivalent. So when N of A is equal to N of B, really it's nothing much into this thing here. So when you have, of course, equal sets are naturally equivalent sets, but not every two equivalent sets are equal, right? Why? Because when the two sets are equal, they are literally equal, means you have the same elements in both sets. Well, if they have the same elements in both sets, they must be having the same cardinal number, and therefore they must be equivalent. But the reverse is not always true. Like this example we just had. The set D is not equal to the set E. Well, the set E has the lowercase letters A, B, C, but the set E has these 3 kind of fruits. Well, you cannot, they are not equal. They are just equivalent. Yep, not all set that are equivalent are equal, like I just said. Here's an example. They talk about the same example I just talked about. So they are equivalent, but not equal. So when you have two sets that are equivalent, you can always create what's called a one-to-one correspondence between the two sets. What does this mean? I'll give you an example. So, and then we can go back to the definition. Look at set S and set C. Are they equal? No, they are not equal because they have different things in them. Are they equivalent? Well, let's count the cardinality of them. S has how many elements? 1. North Carolina is just 1 element. Don't say 2 words. Remember, the elements are separated by commas. If you say, for example, the first element could be the beautiful North Carolina, it will be just 1 element. But here is North Carolina, 1 element. Georgia, 2nd element. South Carolina, the 3rd element. Florida is the 4th element. So the cardinality or the cardinal number of S is 4. 1, 2, 3, 4. Well, how about C? Columbia, Raleigh, Tallahassee, Atlanta. So also 4. So these two sets are equivalent. Now, can we build a one-to-one correspondence? Yes, you can. One-to-one correspondence means every element of one set will be paired with an element of the other set. For example, I can say North Carolina will go with Columbia, Georgia will go with the Tallahassee, South Carolina will go with Raleigh, and Florida will go with Atlanta, right? So you can like pair them. Well, don't say, no, Florida should go with Tallahassee. I'm not referring to Tallahassee to be the administrative capital of Florida. No, I'm talking about this from a math point of view. If you have two sets with the same number of elements, you can create pairs, or you can create what's called a one-to-one correspondence. And here's an example of a one-to-one correspondence. I matched North Carolina with Columbia, Georgia with Raleigh, South Carolina with Tallahassee, and Florida with Atlanta, for whatever reason, right? Or we could have done this one-to-one correspondence. But if you have two sets that are not equivalent, it's impossible to have one-to-one correspondence. So for you to have a one-to-one correspondence between two sets, the two sets must be equivalent. In other words, the two sets must have the same number of objects. Well, consequently, I can tell you now that two sets that are equal, they're always, you can always put one-to-one correspondence between them, right? Well, what you can, this is, we can skip this slide without any damage. This is very important. There is a special set. Oh, still a set. A special set is a set. But this set has no element. You open the curly braces, you don't put anything, you close it right after. So this set here that you see, this one here, this set here is a set of no elements. It's called the empty set, yeah, the empty set, right? And also it's called the null set. Some people, some mathematicians, they were not happy with this notation. French mathematician, 19th century, and they create a symbol for this. They put a circle and they put a bar through it, right? This is the same thing as the empty set. So when you are asked to write down or symbolically represent the empty set, you have two choices. Either you put two curly braces with nothing between them, or you put a donut and you slash it with a, with a line segment, or a circle or line segment. So that group, French mathematician called the Bourbaki group, in the 19th going to 20th century, it's French mathematicians who did a lot of work in mathematics, but the symbol is created by them. Well, we are going to have something that may not be clear to all of us here. Let me go back to this. If you have a curly brace and then nothing and a closing curly brace, this is called the empty set. The moment you put something in between, it's not an empty set. It's a set that contains whatever you put in between. Particularly, this one is not the empty set. What is this? This is a set of one element, and that element happens to be the empty set. Remember, when you are asked to create a set, there is nothing that tells you that the object should be of this type or that type. In a set, you can put anything. Well, anything, really anything? Yes, you can put a set within a set. Here, this set here is a set of cardinality 1. And if someone asks you, what is the nature of that object, of that one element, it says the empty set. I'm free to do that. For example, I can have this set here. Look at this set. This set 1, 2. So this set has how many elements? 4 elements. What are these elements? 1, 2, and the third element happens to be a set by itself that has 1 element. Do not confuse this by itself and this one here. These are totally different animals. This is the element 1. This is number 1. This is a set that has 1. And the fourth one is the empty set. So if I call this set A, the cardinality, n of A is what? Is 4. How about this set B? 1, 2, 3. How many elements? What is the cardinality of B? Okay, pause this now and answer this before playing it again. What is the number of elements, or what's the cardinal number of B? Okay, I hope that you paused it and now you're back. Well, it's just 1. Don't say 3. This is the set B that has 1 element, and this element happens to be a set of 3 elements. Remember, you're free to put whatever you want to put as objects or as elements of a set. So consequently, when I go back to this, this is a set of cardinality 1. Yeah, that's what it is. This is the set of also of cardinality 1. These two sets are equivalent, right? Because they are both having the same number of elements. Okay, so just pay attention to this little small point here. When you do homework, there are plenty of exercises that will show you how to deal with this situation. Again, when you go into your homework, and if you're stuck, there is a button that says, show me how to do this, and there's a video. Most likely you find a video. If you really stuck, and you are very welcome, of course, to shoot me an email and can meet over Zoom and give me a call sometimes. You like the little small things, you can clear them right away. So you don't have to be formal and send me an email and back and forth. Sometimes small issues can be cleared over the phone real quickly. So I let you decide how to contact me. For me, it does not matter, really. You are very welcome to call, to text, or to email. A universal set. In some exercises, you may list all the elements that you are going to be working with in that exercise, and this is called the universal set. So the universal set, sometimes you use the symbol capital U, contains all the elements for any specific discussion. I can have, for example, my universal set to contain 1, 2, 3. Means in this exercise, the only elements I'm going to deal with are 1, 2, 3. Or I can have my universal set to be equal to set n, the set of all natural numbers. So really, the exercise should tell you the universal set. So you cannot, nobody will ask you what is the universal set, because it depends on the discussion you're having. It depends on the question you're dealing with. So that's why it says when the universal set is given, only the elements in that universal set might be considered. You cannot just bring something outside of that. So if you have an exercise that tells you, okay, well, here's your universal set in this exercise, which is 1, 2, 3, means you cannot talk about 4, you cannot talk about birds, you cannot talk about monkeys. The only elements that you can talk about are 1, 2, and 3. That's it. So again, it's pretty straightforward, right? So if I take the universal set to be 1, 2, 3, all the way till 10, the only natural numbers I can talk about is 1 through 10. I don't know 11, I don't know 12, I don't know -17, I don't know 1.2. Only I know 1, 2, 3, 4, 5, 6, all the way till 10. Okay, well, that was our first section. We talked about sets, we defined some symbols, element of, not element of. So I think you can now go and tackle the first homework, section 2.1. And after that, then go back and watch the lecture on section 2.2, and you good. And then after that, you can go to the homework and you get the I would say the drill, right? And then once you finish all these sections, go and do your test for that module and move to the second module, which is about logic. Okay, take care.